Hi again. Let's talk about the EKG reading on the heart. Before I get into the slides, I want to describe in a way the action of the heart. Keep in mind that the atria contract first and then the ventricles. And the atria are on top, they contract first and then the ventricles contract. So it goes top, bottom, atria, ventricles, pause. That's when the heart's at rest and filling. So it goes top, bottom, top, bottom. That's the heartbeat. That's what's happening every time the heart beats. It goes atria first, ventricles second. So that's what we're looking at. So think of it as sort of top, bottom, atria, and then ventricles. And there's a little bit of a pause. The ventricles have to delay when they contract. So remember that the SA node starts the cardiac cycle. That fires first, the pacemaker potentials. The atria contract first, then there's a bit of a pause, and then the ventricles contract. They don't both contract at the same time. Okay. So this slide is just your basic introduction to reading an EKG. And EKG and ECG are the same thing. EKG comes from the way the German Deutsch spell cardiac with a K, English spell cardiac with a C, but they're the same idea. They're used interchangeably. So something to note when you're looking at this, what you see, what's prominent is you see a large spike. And what you need to appreciate in this picture in interpreting and sort of understanding ECGs is that that is not an action potential. It is not. So don't think that. Actually, what that spike represents is all of the electrical activity that reaches the surface of the skin. Because when you do an EKG, you put a little electrodes on the surface of the skin around the body, and those electrodes pick up electrical current that reaches the surface of the skin. So the electrical signal originates deep in the chest from the heart muscle, and then that electrical signal propagates outward in all directions through the salty water of the interstitial fluid out to the surface of the skin, where it is then detected by the EKG electrodes. So this, what we're looking at on an EKG, is the sum of all the electrical activity measured at the skin. So it is not the same as an action potential. It takes a little while to kind of get used to that idea. And along those lines, that the waves, the bending of the tracing, either up or down, indicate the net ion movement across cell membranes. So it's the net ion movement across the cell membranes of the heart, and that signal reaches the surface of the skin. So what's key to remember is that the idea is that this is the net ion movement across the membrane. If there is no net ion movement, then the line is flat. So for example, here it's flat. Well, what's going on there? This is the period when the heart is at rest. It's not contracting. The skeleton or the cardiac muscle is polarized. This is the RMP. There's no net ion movement. The sodium channels are closed, potassium channels are closed. There's a little bit of leakage, but we're sitting pretty stable at our resting membrane potential. So that's the flat line. So keep that in mind as we go along. A couple of other things to note. If we're talking about an interval an interval includes the wave. So for example, the PR interval is between the P wave and the R wave. And that is the PR interval. What I'm getting at is that it included the P wave. So the way the EKG reads, maybe I should have gone over this first, is just in alphabetical order. The first event is the P wave. We'll go through this. So it goes P, and then there's a Q where it drops down, and then an R wave at the top, and then an S. And that's referred to as a Qrs complex. So there's the highlighter. Includes the Q, the R, and the S. And then the last thing is the T wave. So they go in alphabetical order: P, Q, R, S, T. Okay, so the intervals include the waves. PR interval includes the P wave. A segment, on the other hand, does not include the wave. So for example, here is a flat segment between the S and the T, and it does not include the S wave or the T wave. So that's an ST segment. So intervals include the waves, and segments do not. So for example, here is the QT interval, and that includes the QRS complex and the T, and it's a period of time that we'll look at in the next figure. So that's the basic picture of the pieces of an EKG that you need to know. I would practice drawing it out on scratch paper and just getting used to the idea of the different waves in a cardiac cycle. So for example, you should practice, there we are at rest. I'm at the bottom left of the screen. And then the first thing that happens is a P wave. And then we have a little dip in the Q, the R, the S, another flat period, and then a T wave. So this was Q, S, and R at the top. And then it's rest. This is diastole. And then you start another heartbeat, another cardiac cycle. P, Q, R, S, T. And after every T, or next thing that would happen, P, geez. See if I can write a P. P, there's the R, and at the bottom would be the Q and the S. So practice doing that. Another thing to note is that on the R wave, so let's just take a look at this for a moment. So here is the P wave. Remember that this is not an action potential. So it won't be helpful to view this rising phase as depolarization and this is repolarization. That is not the case. All we're saying is that during the P wave, ions are moving. So if you think about it, what happens when a cell depolarizes? Like myocardial muscle cell. What's the big ion event when it depolarizes? Well, it's the flood of sodium into the cell. So sodium is moving into the cell, and there's a net movement into the cell. And then at the top of the action potential, remember that the sodium channels close. And they close, and then there is no more movement of sodium. And we're back here at the bottom. But as we'll see, the atria are still contracted at this point. So this is not repolarization on the EKG, not repol. Okay? It's not an action potential. It's showing the net movement of ions. If ions enter and then they stop entering, we're back to the flat. The same thing you could appreciate perhaps if we look at the plateau phase of a cardiac muscle cell, contractile myocardial cell. There's a steep depolarization, and then we had this plateau phase, and then a repolarization. During this phase, that plateau phase, the sodium has entered, and then it stopped. Calcium has entered, and there's not a lot of net movement. And at that point, the line is going to be flat. Don't worry about all this coming together at you in a giant hurry right now. We're going to go through it. But during this plateau phase, there is very little net additional ion movement, and we get a flat line. And then when we go to repolarize, then the ions start to flow again, the potassium starts to leave, and we get the repolarization as shown here. So this is repolarization. This is not. It's just the end of potassium movement. Okay, so play with that, ask questions. I think you'll do okay if you practice. The main thing from this slide is to identify the major waves and segments on an EKG. So it goes P, Qrs Complex, and then a T. And the two intervals that you should pay attention to, or the one interval, is the PR interval and the QT segment. But it's mainly the PR interval that I'm going to work with mostly. Okay? Actually, let me get rid of that and include the interval, not the segment. So it's this one, PR interval. Okay, so we'll talk about that some more. Let's keep moving. Next slide. And here we're talking about the electrical activity and how it's correlated with the mechanical activity. So this is the pumping of the heart. This is the contraction of the heart. And the two are correlated. They're connected. So the electrical activity drives the mechanical activity, like wires to a motor, if you will. Okay, so here's what's important. You know where the P wave is, and the P wave, that's the electrical piece of the story. Well, the mechanical piece of the story is that the P wave starts atrial depolarization. So that P wave is where the atria depolarize, and that begins the start of contraction or atrial systole. And to start the P wave, remember the SA node. That's what starts the cardiac cycle. So the SA node fired, that caused the atria to depolarize and contract. And that's what happens during the P wave. The QRS complex is correlated to ventricular depolarization. So the QRS complex is the electrical activity is the ventricles depolarizing, and then that starts ventricular contraction. And then we have ventricular systole. Okay? So we're going in order. So we have the atria contract, and now we have the ventricles contract. And the ST segment from S to T, ST segment, what is going on there? That is the period of the plateau phase, when the ventricles are contracted. So the line is flat on the EKG. This ST segment is generally more or less flat. The ventricles are depolarized. They're holding it. That's that long plateau phase. And then the T wave is associated with ventricular repolarization and relaxation. So during the T wave is when the ventricles are repolarizing and relaxing. And that leads to relaxing or diastole. And then we are back to this period of rest. Heart's not beating. Then you'd start over with another P wave. So the PR interval, number 5 on our diagram, the PR interval is the amount of time. So think about what's happening with our electrical conduction system. The SA node fired first, and the signal rapidly spread through the atria and they contract, and the signal is rapidly sent to the AV node. But then at the AV node, there's a pause, there's a delay, and that's what allows the atria to finish their contracting before the ventricles contract. It makes for more efficient pumping of the blood. So the PR interval is the delay. It's between the P wave and the R wave. And the P wave is generally pretty easy to spot on an EKG tracing. It's the first deflection, and the R wave is the most prominent feature of the EKG. So it's pretty easy to pick out the R wave, and then you find the start of the P wave and measure that time, and that is the PR interval. And a normal PR interval is in the range of 0.16 to 0.2 seconds. So you should also be able to tell me how many milliseconds 0.2 seconds is equal to. And if you said 200, you're in good shape. And if you would like to do that, let's just do it just for review, because I am going to ask you to do unit conversion problems of this type. So let's go ahead and do that. Let's convert 0.16. So let's convert 0.16 seconds to milliseconds. I'm going to get this bar out of the way here. So you know, hopefully, how to set these up. If not, you should practice. Let's start with what we have, 0.16 seconds. And we're going to multiply that by some conversion factor that relates seconds to milliseconds. So what you have to have memorized is that 1 second equals 1,000 milliseconds. Okay, so we're starting with seconds. We want to get to milliseconds. So we're going to multiply it by this conversion factor. And we want to be able to cancel units out appropriately. So let's put the seconds on the bottom. And we'll put 1,000 milliseconds on top. And once we have that set up, then we cancel out the seconds. That's good. And we're left with 0.16 times 1,000. And you just move the decimal place. You know which way you're multiplying. It's going to get bigger. So it is 160 milliseconds. 0.16 times 1,000. So you would move it, multiply by 10, by 100, by 1,000. Okay, enough of that. Hopefully you remember that. If not, practice it. And if I have some time, I'll post a series of practice problems for you to do. In fact, note to self. Okay. Next slide. And here is just practice looking at an EKG on a grid line. So all I'm after here is that you know that each large square represents 0.2 seconds. So here is 0.2 seconds. It's 5 millimeters. So that line to that line is 0.2 seconds. Zero 0.2 seconds. 200 milliseconds. And each small square represents 0.04 seconds. And there are 5 small squares and 1 large square. And you should be able to complete this unit conversion problem again to show that 5 small squares are equal to 1 large square, of course, and 0.2 seconds. So you should practice this conversion problem and come up with the correct answer. If you have trouble, let me know. We can deal with that during office hours. I can pull up this board and we can work some problems if we need to. Okay? Next slide is practice. Let me move the bar out of the way here. Okay. So here's some problems to think about. It says, how many small squares would be present in the shortest normal PR interval? So the first thing you need to know and remember is, what is a normal PR interval? That you need to memorize. Remember? The PR interval normally is between 0.16 what? Seconds or milliseconds? Seconds. And let me change that to 0.2 seconds. So that you need to memorize. A normal PR interval. So you need to know how many squares that represents. Okay? So the problem is, how many small squares would be present in the shortest PR interval? Well, the shortest PR interval would be 0.16 seconds. So if we started with 0.16 seconds and multiply that by how many seconds in a small square, we want small squares because that's what we're asked for. How many small squares? So we want small squares in our answer. So it's one small square. I'll abbreviate small and square. How much time is that? One small square is equal to 0.04 seconds. All right? We can now cancel out the seconds, and we're left with 0.16 divided by 0.04. And do the math on that, and hopefully we'll wind up with 4 squares. 4 small squares. So, if you're looking at an EKG and you find and identify, mark out carefully the PR interval, how many small squares? Let me back up to the previous slide. So let's just practice this. So we want the PR interval. We'll use this last cardiac cycle on the right. So what's the PR interval? Let's see if we can get that. So here's the start of the P, and there's the R, and it looks like it's pretty, my red line's drifted a bit, but it looks like it's pretty much one large square. So that would be 4 small squares or one large square. So here the PR interval is what? Okay, so you want to practice doing that. Back to where we were on the other slide. If you counted 7.5 small squares in a PR interval, what would the time be? So again, you would have, now we're given 7.5, 7.5 small squares. And we need to convert this to time. So we know that one small square is equal to how much time? 0.04 seconds. You have to include the units. So write down seconds. And then we can cancel out the small squares. And we're left with 7.5 times 0.04 seconds. Use your calculator if you want to, and you should come up with a time of 0.3 seconds. For, what was this? This was our PR interval. Is that normal? No, because it's outside this range of 0.16 to 0.2. So it's quite a bit longer than normal. So that could be a problem. Okay, last problem. If you counted 4 large squares and 3 small squares between 2 R waves, how much time? So the picture would look something like this perhaps. So what do we have? 2 R waves we're going between. So let's just draw in a couple of cardiac cycles. Something like that. There's one. So there's the P, there's the R, and the T. We'll draw another cardiac cycle. P, something like that. There's the R. And the time between these two is, what did we say? We count up, we have 4 large squares and 3 small squares in this time frame from here to here. We just counted up the squares, that's what we got. How much time is that? Well, let's get this out of the way. You can do this. Probably getting bored perhaps, but let's do it anyway. We have 4 large squares. 4 large squares, and they are equal to 0.2. So if we multiply 4 large squares times 0.2 seconds per square, we should wind up with 0.8 seconds. And then we have 3 small squares, and those are equal to 0.04 seconds per square. Do the conversion and you wind up with 0.12 seconds. So add those together from R to R, and we wind up with 0.92 seconds per beat. In between beats. See if you could then convert that to heart rate in beats per minute. We're going to get there, but we don't need to do everything right now. Okay? Last slide, which is an easier way to calculate heart rate rather than what that is showing. Oops, hit the erase button. Oh well, yours is already recorded. So this slide shows just an average, general, normal sinus rhythm. And what you might notice, well, you should be able to identify the P's, the T's, and the R's. Those are pretty easy. And then you have the Q and the S. But the significant features are the P, the R, and the T. Okay, so the question is, here comes the strip. It's right off the EKG machine. Your patient's right by your side. Maybe you're in an ambulance racing to the hospital. Maybe you're up on the floor and you're just monitoring the person. And the first thing you need to do when looking at a heart rate is figure out what the heart rate is. We already determined that it looks fairly normal at quick glance. That's good enough for right now. So what's the heart rate? Well, the easiest way to do this is to mark off 6 seconds. So you notice that on this EKG, there are these tick marks at the top. And these are a little bit taller than the others. And then how much time is between each one of those tick marks? Well, there are 5 large squares. 1, 2, 3, 4, 5 times 0.2 seconds each. That's 1 second. And between the next two is another second, etc. So 5 large squares equal 1 second. That makes it pretty easy. So all you have to do when to rapidly determine a heart rate is to count out a 6-second strip. So we'll start here at 0. There's 1 second, 2, 3, 4, 5, 6. Done. Count out how many beats are in that 6 seconds. Well, there's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 beats. In how much time? 6 seconds. We want this in beats per minute, not beats per second. So we get rid of seconds and convert it to minutes. So there are 60 seconds in 1 minute. Good. Cancel out the seconds. And 6 goes into 60 10 times, right? So we're left with 10. And voila, we have 8 times 10. You can do that in your head, and that's 80. 80 what? Don't forget the units. It's beats per minute. So, do this in your head. What if you had 6 R waves in a 6-second strip? Be 6 times 10, it would be 60. If you had 12 beats in a 6-second strip, it would be 12 times 10. You can do that in your head. It's 120 beats per minute. Okay, that's it for basics of an EKG. We'll come back to interpreting some common patterns at the end. So I hope this helps. Do practice and ask questions when you have them. I look forward to questions. I like them.